Hello and welcome to Chapter 2 in CHEM24. In this chapter we'll be talking about atoms and molecules. So what are the objectives for this chapter? Well, we'll define lots of terms that we'll be using for the rest of the semester. Atom, molecule, what's an isotope of an element, then how do you form an ion, what is a compound, and then at the very end a little bit of engineering stuff. We'll talk about plastics, so polymer, how you make a polymer from monomer, and what are some of the organic functional groups. And within this, we'll describe the nuclear model for the atom, right? How it's composed of protons, electrons, and neutrons, and then how you can recognize a particular isotope, right? We'll talk about chemical symbols. Then if an element has various isotopes, you'll see that those will each have a different mass. How do you calculate the average atomic weight? Then we'll explain the difference between what's a molecular formula and an empirical formula. There's more, right? And then we'll also look at how can you take the number of atoms, right, that there is in a molecule by looking at this chemical formula. And then for the first time we'll be introducing, the periodic table, where the various elements are there in it, and then why is it tremendously useful. Then at the very end I'll talk a little bit about organic chemistry and then how to convert, chemical formula into a line drawing and vice versa. And then what you will not enjoy, but this is just part of it, you have to learn how to say the names of compounds, and so standard chemical nomenclature is going to be a big part of this chapter. And then we'll wrap up with a little bit of polymer chemistry. And so how does the atom look like? You know that all the matter that we're concerned about, at least in chemistry, is composed of atoms. Okay. Now the atoms have a nucleus, and that is, here in the center, and it contains protons and neutrons. The protons are positively charged, and the neutrons are neutral here. And so the nucleus therefore is positively charged because of the protons, and then no matter how many neutrons you have in there, the charge does not differ. And that's very important because the nucleus is surrounded by the cloud of electrons, and the electrons are negatively charged. In fact, not just negatively charged, but they have the same exact charge as the proton, right? It's an elementary charge, we call it. And therefore, for an atom to be electron neutral, you have to have the same number of electrons as protons. And we'll see later that all of chemistry is coming from the number of electrons, and therefore it does not matter how many neutrons you have, because neutrons don't change the charge, and therefore they will still have the same number of electrons. And so this kind of looks like a little bit of a solar system, except of course the planets don't go in these weird orbits. But what we'll have is this nucleus in the center, and then around the nucleus we have the electrons flying around. Now, in the currently accepted model of the electronic structure, the electrons don't quite travel like this. It's not like the planets around the nucleus, but it's more like this. It's more like a cloud. And so their center is nucleus. It's actually much smaller. It's about 100,000 times smaller than the atom. Now, what is 100,000 times? You can picture it as if the electron cloud is a mile long, right? A mile in radius. Then the nucleus is like the size of a grape. Okay. And so the nucleus is very small compared to the size of the atom, and this largely empty space outside of the nucleus is filled by the electrons flying around, and then the density of the electrons is related to the probability of finding electrons at particular locations. So what we'll say is, unlike the previous picture where it shows that the electron travels like this and round and round, instead we will only know a probability distribution, like a cloud of the electron around the nucleus. So let's see, how many? right? And that's the most important number here when we describe an atom. And the atomic number is how many protons you have in the nucleus, which identifies the element. And since the electron and the proton has the same charge, just opposite, it also equals the number of electrons in a neutral atom. And since chemistry is coming from the number of electrons, then really the atomic number determines, what element it is and how it behaves chemically. Now, the mass of an atom, of course, is very, very small. And so instead of using, grams and stuff like that, we'll be using also what we call atomic mass unit, or AMU. I think that they have a different symbol for it, whatever. And the proton is 1.007 AMU. The neutron is 1.009 AMU. So the neutron is slightly heavier than the proton, and the electron is about 2,000 times lighter than either of them, right? So the electrons are very, very small. So most of the mass of the atom is in the nucleus in the form of protons and neutrons. The number of protons equals the number of electrons because they're oppositely charged by the same charge. Now, as I said, the neutrons are neutral electrically, so they don't carry a charge, which means that if you put more neutrons into the atom, its chemical identity will not change because the number of protons and therefore the number of electrons is still the same. And so you can have atoms of an element where the number of neutrons is different in the nucleus, but otherwise they're identical. That is, the same number of protons and electrons, so it's still the same element, but the nucleus has a different mass. And so some elements are monoisotopic, which is technically, okay, whatever. So there's only one number of neutron in it. For example, fluorine is like that. But then most other elements have more than one isotope, and there are percentages for each isotope. What are the relative amounts? And then this is what we call isotopic abundances. And this is kind of important. And then one way to measure it is with, well, the best way to measure it is with mass spectrometry. What happens in a mass spectrometer is you're forming positive ions. Somehow, one way to do that is to use an electron gun, for example. And then what happens is if you take a molecule or an atom and then hit it with an electron, then you're forming a positive charged species and then two electrons flying away. Why is that? You would think that if something catches an electron, it will be negative, right? Because the electron carries a negative charge. But what happens is that the electron has a lot of energy, so it's like kicking out another electron. And whatever it happens, it means that will form something that has a positive charge on it. And then it means that I can fly it in an electric field and then I can deflect it in a magnetic field here. So this is what we call a magnetic sector mass spectrometer. And then when it flies, then it will go through an exit slit. And then if I change the deflection by the magnet, or actually the way it's done is changing the acceleration towards the magnet, then different masses will turn differently, and therefore only a certain one of them will go through the slit and get detected here. I'm not sure what this thing is at the very end of it. Maybe it's the connector, but anyway, so what it will give you the information is where you will scan with, do I see ions with this, do I see charged particle with this mass, that mass, and then suddenly you see a bunch that has a mass 12 in AMU and then some in mass 13. And so this means that carbon has two isotopes. I can have carbon 12 and I can have carbon 13. Now, what does it mean, carbon 12 and then carbon 13? It means that carbon has 6 protons, and then the carbon 12 has 6 neutrons and 6 electrons. And then carbon 13 has still the same 6 protons, but now 7 neutrons and also 6 electrons, right? Because the mass is roughly equal to 13, not exactly 13. Well, it's exactly 12, right? And then and that shows, the 13 is the sum of the neutrons and the protons. But how do we write this down? What are the symbols that we use? And so the atomic symbols use the following convention. So in the center, we put the symbol of the element, which is always, a capital letter and possibly a lowercase letter next to it. For carbon, it's just C, and then you also see those symbols on the periodic table. Next to it, you can put these two numbers. So the lower one is kind of optional because it shows the number of protons and therefore the atomic number. And then the one here is the mass number. The mass is coming from the protons and neutrons, and so this number is the protons plus the neutrons, and then this number here is just the proton. So if you take the difference of the two numbers, that will of course give you the number of neutrons. And then here, and that's why I'm saying that the Z is optional, because from the element's symbol you can determine the atomic number and vice versa, right? As we'll see soon on the periodic table. Now, what are these atomic symbols? Well, you've seen many of them. Very often they coincide, the symbol with the couple of letters in its common name in English. But of course, sciences were established long before this country, and so for some of them they have nothing to do with English names. So for example, gold is AU, which is Latin for Latin aurum. Iron is coming from ferrum. Lead is plumbum. What profession does it correspond to? Plumber, right? And so because plumbers use lead pipes, and therefore the connection. And mercury is Ag hydargium, or argentum for silver, and then and these are all Latin names, but sometimes it's this, for example, is the same as the German name. So in German, sodium is called natrium, and then Na therefore is the similarly potassium. K is actually kalium in German. Right? A lot of the early chemistry, especially, but even 20th century chemistry was done in Germany. Okay, so what if you have an element, right, and then it is not just one isotope but several isotopes, right, and they have a certain proportion, and therefore the atomic weight has to be some sort of a weighted average of all these, and so this is what we will call as atomic weight, and it's a weighted average of the individual atomic masses of its naturally occurring isotopes. So for example, carbon-12, which is 6 protons and 6 neutrons, its atomic mass is exactly 12, and then it has a 98.93% proportion ratio, right? Carbon-13 has this mass in AMUs, and it has 1.07% of the total, and then when you add it up, then you get the weighted average mass. And it's the exact same procedure as calculating your GPA, right? You look at the how many A's you have, how many B's you have, in terms of units, and then you take the weighted average, an A is a 4, B is a 3, and so on, and then you add it up and you get your GPA, if you ever want to calculate it. So similarly, the average atomic mass, or the atomic weight, is this weighted average of the isotopic masses. And then from now on, what we'll do is, since any macroscopic sample of carbon will have this ratio, right? It really averages out this ratio of the isotopes. Instead of calculating with each one separately, we'll just use this average atomic weight in all our chemistry calculation, and for us, one carbon will have this average 12.011 AMU. And you can read this from the periodic table. And so typically the atomic number is given together with the symbol of the element and the average atomic weight. And then if you look at this, you can read all this information. So that Z is 6 in this case, the symbol of the element is C for carbon, and then in our chemistry calculation the atomic weight we'll use is 12.011, which is coming from roughly 98.9% carbon-12 and 1.1% carbon-13. So let's see if we can do a quick calculation here. So we have chlorine, and then chlorine has two isotopes. One is chlorine 35, and the mass is 34.97, and then the other isotope is chlorine 37, and and the mass is 36.95. Now, how much do we have? We have 75.77% chlorine 35, and then the rest is chlorine 37. So how would you calculate the atomic weight of chlorine? So again, this is that usual weighted average, and so I take that 75.77% of chlorine is in chlorine 35, which is 34.97, and then the rest is carbon 37, and that will be 24.23, right, percent, because 1 minus that, and the mass is 36.95, right? And then when you add this up, these two, what you get is, if I manage to turn on the calculator, 0.7577 times 34.97 plus 0.2423 times 36.95, and I hit enter, and then I get 35.4498. And then since they were all rounded to less than that, let's say I have 35.945 is the atomic mass, and this was AMU. Now, if you look at the periodic table, this is indeed what you will read for chlorine. And let's just see if this makes sense, right? So we have the 35, and then we have the 37, and then this is roughly 25%, and this is roughly 75%, right? And so it's indeed the average should be somewhere here, 3 times as close to 35. So 35.5 is a very good estimate for the atomic weight of chlorine. Now, if you look at the periodic table, you see some elements, for example, and let me draw a clear line here, bromine. And if you look at the average atomic mass, it's roughly 80. And then the truth is that bromine has two. It has bromine 79 and then bromine 81, but they're roughly in a 1-to-1 ratio, and so therefore average out to about 80. But when you look at the period, you would think that bromine is predominantly 80, but it actually doesn't have that isotope. It's half and half of 79 and 81. Okay. Now what happens? So we've talked about the number of different number of neutrons and what's in the nucleus and all that. But what about the electrons? What if you have a different number of electrons than the protons? What if the atom is charged? And we'll call this a cation when you have a positive charge. That is, you have more protons than electrons. And then if you have an anion, it means that you have more electrons than protons, and therefore you have a net negative charge. Okay, so negative ions we'll call anions, and positive ions we'll call cations. And I'm sure you've seen this before. And then if it's related to just an atom, right? So you take an atom and the atom has a charge on it, then you have a monatomic ion. Okay, it's from a single atom, but you can also have a molecule, and the molecule can lose or gain a charge. For example, what mass spectrometry does oftentimes is takes a molecule and then strips off an electron to make it into an ion, so then it can be analyzed, and then we will call it a polyatomic ion. Now, some polyatomic ions are actually very stable, and you'll see that those form ionic compounds that will be tremendously useful, and you've probably heard about it. There was a huge explosion recently in Beirut, in Lebanon, and there the substance that blew up was ammonium nitrate. And ammonium nitrate is consistent of two polyatomic ions, ammonium and then nitrate ions. Ammonium is a positively charged, so it's a cation, and then nitrate is negatively charged, so it's an anion. And when the two come together, they can form an ionic compound. Okay, so what are some common ions? So when we look at monatomic ions, it's actually, the naming is very simple. You just take the name of the element right here, and then you add ion, right? So Sodium ion, lithium ion, potassium ion, these are all singly charged, so it's a 1+ charge. Magnesium is a 2+ charge, and aluminum is a 3+ charge. And when we look at the periodic table, you understand soon why. Now, how about negative ions? So similarly, these are all singly negatively charged. Fluoride, chloride, bromide. In this case, you take the name of the element and then add "ide" to the very end of it, unlike in the positive ions. And then sulfide, for example, sulfur, and this is doubly charged. And then nitride ion is a nitrogen with 3 negative charges, right? 3-. Remember, for some reason, I think it's some teachers teach it backwards. It's not N-3, it's N3-, right? The minus is, the symbol for the charge, and then in front of it is how many of those, right? How many plus signs you have, right? It's not +2, it's 2+. Okay, so just a bunch of people do it backwards. Okay. Now, you know that an element, right, and its ion have the same number of protons, and therefore they have the same chemical symbol, but they have different properties because they have different number of electrons. So, for example, if you take sodium metal, you might have seen sodium metal. It's a popular experiment because it's crazy violently reacting with, let's say, water when you drop it into water, and but when it when it loses an electron, gains a positive charge, then it forms a sodium cation, which is the Na+, and that's what you have in table salt. Okay, so it's a very, very, very different species. Chlorine gas, similarly, when it gains electrons and then it forms chloride anions. There's a typo here, oh my god, and it's Cl-, right? And then the chloride is part of table salt as well. It's sodium chloride, but chlorine gas is very different. It's a gas and it's toxic. It was used as a gas in warfare in the First World War by the Germans. That's no fun. And then when you put the sodium cation and the chloride anion together, then they form a salt. Sodium chloride is what we call table salt, and it's a nice benign compound. It dissolves in water. It's a solid. It's colorless, and it has a salty taste. Okay, so now what we'll do is talk a little bit about how we can put together chemical formulae, right? How do we describe a compound in terms of what elements and how many atoms of those elements it has? And so in general, a chemical compound is a substance. It's a pure substance. You make it out of atoms of more than one element, and they're joined together by chemical bonds. And we'll talk about what kind of chemical bonds there are. And in general, compounds, they have different properties than their constituent atoms. So for example, hydrogen gas, oxygen gas, but when you put them together, you get water, which is very different. Now, in general, ionic compounds are kind of special because what they contain is positively charged and negatively charged ions, and they're usually arranged in a lattice in a solid state where the cations are surrounded by anions and vice versa. So the attraction between them is the driving force for creating these. And the way to describe, the molecule or compound is the molecular formula tells you how many atoms, the number of atoms, and then what elements do you have in one unit of a compound. Now, if we're talking about, later we'll define these terms, a covalent compound, let's say water, then one molecule of water has 2 hydrogens and 1 oxygen, therefore we call it H2O. Okay, an empirical formula, or let me give you another example. C6H6, that's benzene. It has 6 carbon and 6 hydrogen atoms, and you put them together in one benzene molecule. But when you just want to say what is the ratio of the 2 elements, what is the relative ratio between the atoms in a compound, you can use the empirical formula, and that is without knowing actually how many there are, we just write the ratio. So for example, for benzene, the empirical formula would be CH, right? Because it just shows 1 carbon for each 1 hydrogen. But it doesn't tell me that 1 molecule of benzene has 6 of each one. I just say that the ratio is a 1 to 1. Okay, and this is kind of important, and we'll do a bunch of calculations with this. Now, this leads us to something that we'll discuss more at the end of the chapter. And if you take this molecule here, ethylene, which is C2H4, the molecular formula would be, this C2H4, right? Because it has 2 carbons and 4 hydrogens. But the empirical formula is only CH2 because it shows that you have 1 carbon for each 2 hydrogens. And then when you take this compound and you polymerize it, then you have these long chains of CH2, CH2 units, and therefore the empirical formula for any sort of polyethylene is still the same, CH2. It just you don't specify how many you have, well, because you don't even know. So how do you write these chemical formulae? You write the types of the atoms, and use for that their atomic symbols, and then what is the number of atoms in each element. You have a subscript to the right. Remember, subscript to the left from the element was the atomic number, superscript to the left was the mass number, right, identifying the isotopes, and now the lower right would be how many you have. Importantly, sometimes it's better to group the atoms, and then you can use parentheses for that, right? And then you have a subscript outside of the parentheses, means that all of the atoms are multiplied by this value. What do I mean? Well, one such story could be copper sulfate. Well, it's a slightly different story. And then what you do is write it like this, which means it has 3 waters. And now what about this parenthesis thing? So let's say, aluminum nitrate. Okay, aluminum nitrate is a compound that has 3 units of NO3s for each aluminum, and therefore the formula would be either AlN3O9, but that doesn't tell you, what form the nitrogen oxygen is in. And so what we use is this parenthesis form where you take the NO3s and then you multiply them by 3, right? And so when you read this, you will know that there are 9 oxygens and 3 nitrogens for each 1 aluminum in this compound, right? So remember, when you see parentheses, then the subscript outside of it will multiply every element in there. Right, so this was about the formulae, how to write formulae, and next we'll be discussing how they bound together, what keeps molecules and these chemical units together. And now that we know how to write formulae for chemical compounds, let's see what holds them together. So let's talk a little bit about chemical bonding. What are the characteristics of chemical bonds? Essentially, what we have is all bonds are created either by exchanging or sharing electrons. Okay, exchanging electron means that one atom of an element gives electrons to another, or sharing means that a certain number of electrons between 2 elements are shared in a common bond. And what this results in is lower energy for the compound with respect to the separate atoms, right? So for example, if you take 2 oxygen atoms, they will be of higher energy than 1 oxygen molecule that are held together by a bond. So what kind of bonds are there? Probably the easiest to understand would be ionic bonds. In an ionic bond, what we have is oppositely charged ions, like say cations and anions, positive ions and negative ions, and they are held together in an extended array which we call a lattice, and since the positive ions attract the negative ions, therefore the lowering of energy. Now covalent bond is kind of different. What happens is that electron or electrons are shared between atoms, okay, rather than one element giving it outright to the other one, but they're shared, and then those electrons are kept in a vicinity of both atoms. And since the nuclei are elected to the electrons, right, the nuclei are positively charged, electrons are negatively charged, kind of like this. So this is one nucleus, the other nucleus, and if you have a bunch of electrons here flying around, right, then both of them are attracted to it, and therefore it holds the 2, otherwise repelling positive charges close to each other. That will be a chemical bond. Another chemical bond is metallic, in which the nuclei give some of their electrons into an extended cloud, and so these clouds move more or less freely throughout the whole array of atoms arranged together, right? And so you have the nuclei with some of their electrons, and then the electrons are kind of like flowing in between. And this means that metals are very flexible, right? Because these bonds are not very directional. While, for example, in an ionic lattice, they have a very well-defined place. So let's see this ionic bonding first. So in ionic bonding, what happens is that an element that doesn't like the electron very much gives it to another element, and therefore you have a positive ion and a negative ion form. Now, why that happens is, we'll see very soon in the periodic table, that sodium has 11 electrons as the atom, and if it gives one away, now it has 10 electrons, and 10 is a very, very good number. Similarly, chlorine has 17 electrons, but when it gains that one electron, it becomes 18, which is also a very good number. We'll see soon. And so what we have is a kind of happy sodium cation and then a chloride anion. And when you arrange these guys in a lattice, you see that this are all sodiums, and then they surround this chloride anion, and so the ions assemble in an array which we call the lattice, and then in this the oppositely charged ions are attracted to each other, right? You see that any given one, let's say this guy, is mostly surrounded by these so this was a sodium and it's surrounded by the chlorides, and then similarly chlorides are surrounded by the sodium, and so the Coulombic force between the oppositely charged particles is what holds it together. Now this Coulomb's law, if you haven't learned it, oopsie, that's some PowerPoint issue here, and so right, 4 pi epsilon naught. Anyway, so the force between two charges is the product of the charges and some constant, well, depending on what unit system you use. And then the important thing is that the force is inversely proportional to the square of the distance, and the energy is proportional to 1 over distance. And therefore, the closer they are and the larger their charge is, right? So it's a product of the two charges, the larger the force in between. One way to visualize this, of course, is this will be the distance between them, and then if you have, let's say, two charges of the same type, like say 2 positive, 2 negative, then it will be a repulsive force. But if you have oppositely charged particles, then the closer they get, the more negative it is, the more attractive this force is between them, and so this is what holds the ions, the oppositely charged ions, together. Right? This is very simple. So all you have to do is one element not liking the electrons very much gives it to the other one. You get a cation and you get an anion, and then these two are then held together, not just two, but many of them in a lattice where the positive ones are surrounded by negative ions and vice versa. Now let's see how a covalent bond looks like. In a covalent bond, electrons are shared in pairs, typically, not necessarily always in pairs, between atoms. So let's look at this water molecule here, just to understand what happens there. Is that, and we will explain this in more detail. But essentially, the hydrogen has 1 electron. So each hydrogen atom takes one of these electrons and asks the oxygen for an electron in return, and then these pairs are formed in which one electron is coming from one atom, the other is coming from the other atom, and now these electrons form a cloud that is mostly between the atoms of oxygen and hydrogen, and oxygen and the other hydrogen, and these electrons hold the two pairs of atoms together, and thereby you form a molecule. Okay, now you can use 1 pair of electrons to do that, and you have a single bond. 2 pairs of electrons form a double bond, and then you can even have 3 pairs of electrons for a triple bond, and in some exotic inorganic compounds you can even have quadruple bonds and beyond. And so this is very useful because unlike the kind of boring arrangement in an ionic compound where it's in a lattice, each atom, each cation is surrounded by anions and vice versa, now you can build almost anything. And so, for example, if you look at this compound, this propane, then the carbon form a chain, and then the hydrogen is on that. And you can build very complex structures with covalent bonds when pairs of atoms are held together by these sharing of electrons. And then this would be an illustration for a double bond, right? Carbon, right? Dioxide, so CO2. They have double bonds between each carbon and between the carbon and each oxygen. Now, the third kind of bonding that we want to explore just a little bit is what happens in metals. So what you have is we distinguish electrons into the core, and then the rest will be in the valence. And then the valence electrons, and we'll explore these later when we get to electronic structure and bonding and all that. But essentially what you have is the outer electrons, what we call the valence electrons, right? They form this sea of negative charge that is kind of free-flowing around the positively charged cores, and then the metal nuclei are arranged in a lattice, and then the electrons more or less move freely. But which means that since there's a lot of electrons who move freely over this lattice, they conduct electricity. They also conduct heat typically very well. And then furthermore, which is very important, imagine what happens. Let's go back a little bit to the ionic bond, right? So what happens if you take this row of ions and then you shift it by, let's say, one atomic distance? It would be a disaster, wouldn't it, right? Because then the this would be a green gray green, and so there would be a lot of repulsion between the similarly charged ions. And so instead here, when you look at this, if you move, let's say, this column a little bit to up or down, nothing really happens, right? Because it's kind of a non-directional force. You still have a cloud of electrons flowing around it, and thereby the metals are very flexible, right? There you can hammer them, you can pull them into strings and so on. And so a lot of the properties of metals that we know directly come from this, how they bond. And so now we're ready to categorize the elements into the periodic table. And the basis of this is what we call the periodic law, which means that if you arrange the elements properly, then they display a periodic variation in their chemical and sometimes even physical properties. And so in this periodic table, right, so this thing, right, we'll have horizontal rows and then we have vertical columns. Okay, this is not very beautiful, but yeah, and then I missed helium. But anyway, so we'll have groups that are vertically arranged, and then we have these horizontal rows that we call the periods. And so the groups that we have names for. The group 1 is the alkaline metals. Then the alkaline earth metals is group 2, the next one. To the right we have the halogens and the noble gases. And then let me just show you on the periodic table. So this is how it looks like. Okay, so the alkaline metals are the first one, group 1. Then group 2 is the alkaline earth metals. Then this is the oxygen group. Or chalcogens, then this will be the pnictogens. This is the carbon group here, and then this here, except hydrogen somehow sneaked in here too in this weird periodic table. This is the halogen elements, and then this is the noble gases. And so if you look at this, then you'll notice that elements that are in the same group, their same column, they have very similar properties. So say sodium, potassium, rubidium, cesium, those are all metallic elements, very reactive. If you put them in water, they would explode. Then they all like to form ions with a 1 positive charge. Then the alkaline earth metals, magnesium 2+, calcium 2+, they are very similar. They form ions with a double positive charge. They're all metallic elements. And these guys, carbon, silicon, they can form various very elaborate structures that are all covalent. Then the properties between oxygen and sulfur, especially selenium, are very similar. Then these guys, the halogen elements, they also behave very similarly. And the other thing is that I've seen before is that every element ultimately wants to be like the noble gases. And so if it has fewer electrons than the noble gases, it wants to gain a few. And if you have more, let's say sodium has 11 and then neon has 10, so it could lose an electron and becomes a sodium ion, right, by losing an electron. So this is how we arrange the elements. And then the periodic table is also very special because which elements are metals and non-metals, they kind of neatly arranged. So hydrogen is kind of a strange one, but there is actually a metallic form of hydrogen too under extreme circumstances. But roughly most of the elements are metallic and on their left lower side of the periodic table, where non-metals are on the right top corner of the periodic table. And out of this, the right hand is the noble gases. And now I drew all over the place. And typically the metals that again are left bottom, they're shiny, they're malleable, they're ductile, which means you can draw them into a wire. They conduct electricity and heat really well, and they form cations. Non-metals, they typically form anions. They're not shiny, malleable, or ductile. They're typically brittle if you try to exert a force on them. They're in the upper right-hand portion of the periodic table. And then in between the two, you have metalloid or semi-metal elements that have properties that are both metallic and non-metallic. And so most of the elements of the periodic table are governed by what we call inorganic chemistry. So in general, organic chemistry is the compounds of elemental carbon, but no metal present. Okay, inorganic chemistry is all other elements that either don't have carbon or the carbon is directly connected to a metal atom. What do I mean by that? So most of the organic compounds are very important in, let's say, biological molecules and all that. Carbon is an element, and later we'll come back to this, which can form very, very complex structures. So you can build really interesting compounds with carbon. And so that's organic chemistry. Inorganic chemistry is all the other elements. The variety between the elements is much larger, but the structures are actually, there's less variety than in organic compounds. Now, in between the two, when there is a metal that is connected directly to a carbon, and whatever is there on the carbon, we call those organometallic compounds, and they're typically part of inorganic chemistry. And I actually started out as an organometallic chemist, so I synthesized and studied a lot of these organometallic compounds. Let's talk a little bit more about inorganic chemistry. And so a lot of the inorganic compounds are typically small molecules, not really like large polymers like we have in organic chemistry. They have covalent bonds in between the atoms. One such example could be, silicon tetrachloride, which is a very reactive compound. It reacts with water vapor and starts fuming and falls apart into silicon dioxide and hydrogen chloride. But anyways, some other elements have ionic structures, right? These ionic lattices, salts, sodium chloride, and the likes. And then depending on what kind of an element is there, the ones in the middle of the periodic table, let me show you here, this part we call the transition metals. And then transition metals, they have variable charge. Since in the periodic table, remember I told you, most elements wants to be like noble gases. But if you're in the middle of the periodic table, then you have no chance for that. And so the rules of how many electrons they can lose for these transition metals to form cations is much less strict. So for example, iron can either be an Fe 3 plus or an Fe2 plus ion, and they can form compounds. So for example, iron 3 here and iron 2 look very different. They're both iron chlorides, but depending on whether it's a 3 plus or a 2 plus, their color is different, their density is different, melting point is different, chemistry is different. This is actually really not a very pure substance. You can see that these parts here are actually already oxidized to iron 3+. So this is not a very good photo, I'm afraid. But anyway, so there are just very many ways that these transitional metal can form compounds, and so there's a lot of variety there. Organic chemistry, on the other hand, is kind of relatively boring when it comes to which elements. It's typically, carbon, hydrogen, oxygen, nitrogen, maybe phosphorus. Not much else. But since carbon is so flexible that it can form 4 other bonds, then they can readily attach to one another. They can form chains. They can form various elaborate structures. And so they can be quite large. These are very complicated compounds, not in terms of what they're built of, but just the kind of structures that you can exhibit. And it would be just a lot of work to write in every carbon and every hydrogen. And so what we can use is this line structure. And in those line structures, we just draw the bonds, but carbons and hydrogens are not explicitly shown. We just have to figure out how many they are, because each carbon should make 4 single bonds, or appropriately smaller number of multiple bonds. And then if the hydrogen is missing, we just have to calculate how many there should come in. I'll show you in a moment. All other elements are explicitly shown. So let's look at this. This compound is called methyl methacrylate. And so this is actually another monomer compound which is used to make a polymer called plexiglass. So what will be the line structure of this? So remember, hydrogens are not included, and then the carbon-carbon bonds are just indicated with a line. So let's start from this corner here, and let's just draw a line for that bond. Then I double line for this double bond here. Then another carbon-carbon bond here. Then a carbon to oxygen bond, and the oxygen is written out. And then another oxygen-carbon where the carbon is not written out. Okay, and then what did I miss? I have an oxygen bound to a double bond. Now, how could I go back from this? And that's the interesting thing. So let me try to switch colors here. That's not what I did. Okay, this is what I need. Okay, so how do I get? Okay, whatever. Let's leave it up there. So this would be a carbon, this would be a carbon, this would be a carbon, this would be a carbon. That is an oxygen, and another carbon. Now, let's see the hydrogen. So this carbon already has a double bond, so it needs 2 more, right? And therefore, it needs 2 more hydrogen. This simply has a single bond, so I can, to have 4 bonds out of it, I had 3 hydrogens. This carbon already has 1, 2, 3, 4 bonds, so it doesn't need any hydrogens. This one has 1 bond, so it will need 3 hydrogens. And you can see that I've totally recreated the exact same structure with the right number of hydrogens. So from this line structure, you can actually derive the formula for the compound, but it's much simpler to write. Again, let me just quickly write it down again, because I overwrote the other one, and then that's it, right? It's much simpler not writing out all the carbons and the hydrogens and such. Okay, now, so this would be good for the structure. But then, interestingly, in organic chemistry, you have these arrangements of atoms, a few atoms in a group that has a certain function that displays a very well-defined chemical property. And so oftentimes we write the chemical formulae to emphasize these functional groups. For example, one such functional group would be the OH group. Okay, the OH group makes something which would only be hydrocarbon on the other side. It would be an alcohol, right? So for example, if I take this methyl alcohol, instead of CH4O, now I write it out as CH3OH, which emphasizes that I have this OH functional group. Okay. Now, hydrocarbons would be the one that don't have any good functional groups. It only has carbons and hydrogens. But if we add functional groups, then we get these most complex ones. Some functional groups, again, this is not an organic chemistry course, and if you need to take it, then it's going to be tremendous fun. Ask anyone. You can take organic chemistry and you'll learn all about this. So carboxylic acid would be a COOH group. Okay, amides, a CO, and then a nitrogen, which typically has a hydrogen on it, and let's say NH, and then it forms a polymer, or it can be an NH2, or it can have more elaborate structures. Let's say aldehydes. And then here, if I put a hydrogen here, that's called formaldehyde. Acetic acid would be one where I put a carbon with 3 hydrogens, that's called a methyl, and then that would be acetic acid. Now, ketones have simply CO and then some hydrocarbon on these two ends. So methyl ethyl ketone, let me just write that one down for you. Okay, C, so that would be the methyl. And then this will make it ethyl. So this is a methyl ethyl ketone, and so on and so forth. So we have these various functional groups that you can put together, and then you can name organic compounds with it, and you know what it is and what properties they have. But let's dedicate the rest of the chapter, and this is going to be the part that involves most memorization. So you may not enjoy it very much, but it's tremendously useful, simply because imagine that if you were to speak a language but you don't know the words, you wouldn't be able to speak the language, right, in the first place. So in chemistry too, you have to learn the words, and the words in chemistry are governed by what we call nomenclature, which is the systematic way of assigning names to chemical compounds. And then in this course, we'll start out with binary compounds, and then even those compounds that have more than 2 elements, there will be a certain kind of simple way to think about them. So let's start with binary compounds, which only contain 2 elements. And let's start with covalent ones, so not the ionic ones. What we first, of course, need to decide is a compound ionic or covalent? And the way to decide is typically if you take a metal and a non-metal together, then it will be an ionic compound. If you have 2 non-metals, they typically find a covalent compound. Okay, and if you have more elements, then we'll talk about polyatomic ions, that typically is going to be an ionic compound, but we'll come back to that in a moment. So let's just say that we have 2 non-metals that form a compound, so it's going to be a covalent one. How do we name these covalent compounds? So first element in the formula will have the full name of the element. Let's say if it starts with carbon, then we'll start the name by carbon. And then the second element is the name of the element, but we add the "ide" to it, just like if it were an anion, even though we know it's not an anion, and we put "ide" to it. But then we also specify how many we have. Because for covalent compounds, you can form very complicated structures, and there's no good way of telling how many there should be. Therefore, we explicitly say it. If there's one of a certain element, we put mono. Let's say carbon monoxide. Okay, it means 1 oxygen. Now, this also right away gives it away when for the first element, if there's only one, we don't use the mono. So if I say mono carbon monoxide, by the way, if the element is started in O, then we just ignore we don't say monooxide. Okay, it would be ugly. Anyway, so for the first element, if it's a mono, then we just ignore it and we call it carbon monoxide. And then we have di, tri, tetra, penta, and so on and so forth. Deca would be 10 of those atoms of that element. And let's see a few examples here between nitrogen and oxygen. N2O, nitrogen monoxide. NO, nitrogen monoxide. Why would I say nitrogen monoxide? Because it will be mononitrogen, but the first mono is omitted. Then nitrogen dioxide. Then dinitrogen tetroxide. dinitrogen pentoxide with 5 oxygens, or dinitrogen trioxide here with 3 oxygens. You can see that in inorganic chemistry there's actually quite a bit of variety too. Between these two elements there's several different arrangements. And then let's just take a quick look at, you remember when we talked about, the molecular formula and the empirical formula? So the molecular formula for this guy is NO2, and the empirical formula is also NO2. For this one, the molecular formula is N2O4, and then the empirical formula is still NO2 like the other one. So the empirical formula doesn't distinguish, right, between these two. Just side note, actually, I recently reviewed an article. Some people did experiments on N2O4, and then they simply called it the dimer, right, of NO2, that you do 2 NO2 molecules together. Let's see a few examples for how to name these covalent compounds. And my recommendation is you post a video here, then you name these yourself, and then once you're done naming, then resume the video and then see if I gave you the same names, and hopefully I did. So let's start with the first one. Here it goes. Dinitrogen pentoxide. Phosphorus trichloride. Remember, there's no mono if it's the first one, that there's only one of it. And then tetraphosphorus hexoxide. Dichlorine heptoxide. Okay, so all you have to do is just look at how many you have and then use those prefixes in naming, especially how many atoms of each element. Now, how about ionic compounds? Naming ionic compounds goes by total different logic. So here it goes. What we can do is, first of all, we will emphasize the charge, right? The charge on the cation, and if the cation that we have in the ionic compound has typically only one common charge, then we'll call it type 1, like say sodium, calcium, aluminum, and zinc. Sodium is Na+, calcium Ca2+, aluminum 3+, zinc 2+, and so on and so forth. How would you know what the charge is? Well, look at the periodic table. The ones in the first column, since they need to lose one electron to go to a noble gas element, then they will be all 1 pluses, like say sodium, potassium, and so on. And then calcium would be, in the alkaline earth metal, so it's always 2 pluses, and kind of like that. Now, type 2s, however, are elements that are somewhere in the middle of the periodic table, and so they have more than one way of losing electrons. So iron can be, let's say, a 2+ charge, or it can be a 3+ charge, iron 2 and iron 3, and then the charge is indicated in the name of the compound rather than how many there are. And then iron 2 with the Roman numeral means 2+, 3 means 3+, and so on and so forth. Now, the anions are then given with the name of the element and I. That's a standard way of naming anions anyways, right? And then if we have a cation and an anion that has more than one element, then it has a common name that we will learn in a moment. So let's see what common cations we should definitely know about. So sodium, potassium, 1+, magnesium, calcium, 2+. Then some transition metals, iron 2 and iron 3, copper 1 and copper 2. Zinc is not really a transition metal in the middle periodic table, but it always is a 2+. Silver is almost always a 1+, so we don't say silver 1, just say silver. And then a few examples for polyatomic ions, ammonium or hydronium, H3O+, and NH4+. When you have these units together with a 1+ charge, that's a polyatomic cation. Okay, so these two are polyatomic. Okay, how about some common anions? Common anions would be the halides, right? Say the halogen elements, fluoride, chloride, bromide, iodide. Then we have a bunch of, let's say, sulfide, right, oxide, nitride, and so on. And polyatomic ones, the ones that you have to memorize: nitrate, NO3 with a 1 minus, phosphate with a 3 minus, carbonate with a 2 minus, sulfate with a 2 minus, hydroxide with 1 minus, cyanide, CN1 minus, hydrogen carbonate. It's the same as a carbonate, but then we add a hydrogen ion, H+, and that reduces the charge to -1, and now we have a hydrogen carbonate. And so what you have to do is you have to memorize the formula plus the charge for each of these polyatomic ions, and that's when you learn these, let's say like learning the words of a foreign language, this is when you can put it together into the name of the compound. Now, there are some polyatomic ions that have a structure they are so common with slight varieties that they have own naming scheme. So for example, when we look at polyatomic ions that have an oxygen in them, then these polyatomic ions we call oxygen ions. And the oxygen ion is first we use the element, the not oxygen element in there, that will give the base name to it. And then the one with the more oxygens, we will have 8. The ones with a fewer hydrogens will have 8. Now, this works well for, let's say, nitrate and nitrite. NO2 with a smaller number of oxygens is 8, the one with more is 8. Or sulfate and then sulfite. But there are some elements where there are 4 possibilities. And if that is so, then for the most oxygens we add the pair, and we call it perchlorate, and the one with the least number of oxygens we add the hypo. So between chlorine and oxygen we call it hypochlorite, chlorite, chlorate, and perchlorate. Okay, so here it's instead of memorizing the names, best is to learn the rules, because it's actually kind of, well, almost logical. Now, example, how would you name ionic compounds? Well, first of all, we need to decide type 1, type 2, right? So this guy is definitely type 2, right? And that means we have to say the charge. How would you name the charge? Well, look at it, and you see that there are 3 oxygens, right? Each oxygen is in the form of an oxide anion, because in the periodic table it's 2 columns to the left from the noble gases, right? So that's a total of 6 negative charges. And then we have 2 irons, and then for the ionic compound to be neutral, it has to have a 6+ charge, right? It's a very important thing, and this is like the central idea, that in each ionic compound, the positive and negative ions have to add up to the same value. It has to be neutral. And so how can I make a 6+ charge from 2 irons is if their charge is a 3+. And now I know that this is iron 3 oxide. Okay, why 3? Because the charge on the iron is 3. Here, second one. It's a type 1 because sodium can only have 1 charge state, so this is simply sodium oxide. Now, if somebody tells you sodium oxide, how would you know that the formula is Na2O? Well, you just look at it and say sodium is an Na+. Oxide is a 2-. Okay, how many Na+s do you need for 1 oxide? You need 2. For the charges to add up, and therefore the formula is this. Okay, and then the third one, calcium again is a type 1, that makes it easy, and so we just call it calcium. And then something to do with nit, right? When you look at it and see NO3 is the higher of the 2, not nitrite, but nitrate, and so we call it nitrate. And since we know that the nitrate is 1 negative, the calcium is 2 positive, and therefore we need 2 of the nitrates, and that's how we put it together. Now, my recommendation is just name everything inside. So look at the end of the chapter, name everything, look at formulae, and find a name for it until it becomes second nature. And after a while it does. It's like when I English is obviously not my mother tongue, but when I speak English now, I don't think about the words, I just say them, and this is how it's going to happen with you, and then chemical naming. Okay, and at the very end of the chapter, there's really not much left, and then this is mostly because engineers are typically interested in new and interesting systems such as polymers, right? I know that it's not just for engineers now, but usually original decors were mostly for engineers. Anyway, so polymers are very large molecules that are made of smaller molecules that are linked together, and these smaller molecules we call monomers. And then we put them together into a long chain of a polymer backbone. So some typical ones, polyethylene, and then we'll talk a bit more about that. Then PVC or polyvinyl chloride, you take vinyl chloride units and then you put together into a polymer. Polyvinyl chloride, polyacetylene, that's a new and then potentially interesting electronic properties. And so each of these polymers have different properties that you cannot find in nature. Now there's of course polymers and plastics have a very bad rap, but simply we can do without them. Anyway, so polyethylene is the most common synthetic polymer, and it's pretty much everywhere, right? In plastic grocery bags, which now the People's Republic of California has banned. Then children's toys, then lots of things because it's a tremendously useful material. How do you make them? Well, you start out with a monomer ethylene, and then you put them into a polymer chain of polyethylene. The way it goes is that you turn the ethylene molecule into a thing called a radical. A radical, as its name suggests, is something that wants to do something radical, and it has an unpaired electron. You know that electrons are stable when they're paired, and if you have a single electron in an atom, it makes it very, very reactive. And so to initiate this, you start with a free radical that attaches itself to this carbon-carbon double bond and makes this initiated radical. And then radical goes ahead and attaches itself to another ethylene monomer, and now you have a longer chain. And after a while, you have these crazy long chains of ethylene. And if you do the polymerization in a controlled way, you can build very, very long non-branch chain of very clean polyethylene that has very good properties and a high density. And in other cases, if the polymerization ends up maybe because you mix something else into it that will cause it branch, you can make a low density polyethylene which has different physical properties. And then if you ultra, you can put ultra into anything, but anyway, so ultra high molecular weight polyethylene has very, very, very long linear chains, and so these have some very desirable properties. So that was pretty much all I wanted to say. And then I acknowledge that we went through the naming very quickly. Typically in other courses, we have a 2-semester general chemistry sequence as well, and there we spend a lot more time on naming. And so at this point, I made a video for that course as well. So I will show you that one if you want to spend some more time on nomenclature, if this is the first time you seriously learn it. But really the point or the trick to nomenclature is just try to name everything. All the compounds you see in the textbook, just try to name it. Or if you see the names, try to write the formulae until you're very comfortable using these rules, which are not very complicated. First you decide whether they're covalent or not, and then if it's an ionic, then whether it's a type 1 or a type 2, is it always just the same charge or a different charge, and then the rest is just balancing the charges to make sure that the ionic compound is neutral. We'll have some practice, and I generally make these competitions of naming compounds, so you have plenty of opportunities to practice. So thank you so much, and that was chapter 2 in Chem 24. Thank you.